Let's now consider this problem from the course. We have a configuration of arrays that are listed up in two parallel subsystems. So if the top subsystem works, then the whole system works. If the bottom subsystem works, then the whole system works. But one of the two subsystems has to work. Now each subsystem only works if if all three of these that are connected in series will work. So if 1 works and 2 works and 3 works, then the whole top works. However, if any of them fail, then the top will not work. Similarly, for 4, 5, and 6, if all 3 of them work, then the bottom subsystem works. Otherwise, the bottom one does not work. So let's figure out the probability that the entire system will function correctly. So the probability that the top works well, we need to have the first one work, and the second one has to work, and the third one has to work. So the probability that the top works is going to be 0.9 to the third power, which is 0.729. The probability that the bottom works well, for the bottom to work, we need 4 to work, and we need 5 to work, and we need 6 to work. That's an AND question, so we multiply. So the probability that the bottom works will also be 0.9 times 0.9 times 0.9, which happens to be 0.729. Same number because we have 3 independent cells on both subsystems. Okay, so now let's figure out the probability that the entire system works. So let me clear out some space on the top. The probability that the system works, well, there's 2 ways for the system to work. The top could work or the bottom could work. Now that's an or question. The top could work or the bottom could work. So that's the probability that the top works plus the probability that the bottom works. Now, in this case, the events are not mutually exclusive. It is possible for the top and the bottom to work, so minus the probability of top and bottom. So this was an OR question. The probability of top works or bottom works. For an OR question, we add, but before adding, we ask ourselves, are the events mutually exclusive? If they can happen at the same time, then we have to subtract something off. Okay, so before I plug in numbers, we have the probability of the top plus the probability of the bottom, so let me copy that here. Now everything's independent. The top is independent of the bottom, and so this and here is a multiplication, just like these were multiplications. And because we're multiplying, because the events are independent, we can just simply multiply blindly without worrying about the conditional probability. So minus the top, or minus the probability of the top times the probability of the bottom. Okay, so the probability of the top is 0.729 plus the probability of the bottom working is also 0.729 minus the probability that they both work, which is 0.729 times 0.729. Now notice the subtraction is important. If I did not subtract that the second term, if I did not take that last subtraction, then I would get an answer that's bigger than 1. Okay, so finally we do the arithmetic. So 0.729 plus 0.729 minus 0.729 times 0.729, we get 0.926559. And that is the probability that the entire system works. So there is our answer, 0.926559.